Okay, so in this video, we will be discussing angular velocity. Now, in normal linear motion, we said velocity is the rate of change of position. So in terms of circular motion, angular velocity is now defined as the rate of change of angular position. It's simply how quickly the angle changes. That is what that definition entails, the rate of change in the angle. Now, the symbol we're going to use is the lowercase omega sign, and it will be in radians per second. Now, just a comment on radians, which I haven't made yet. Radians is a dimensionless quantity. So in other words, we indicate that it's so many radians, but it's just like 2 pi. So it doesn't really have a unit that is attached to it. So according to that definition, we can then have the formula where angular velocity is the change in angular position over time, the rate of change in angular position. Now, what I want to draw your attention to, guys, is that we can also relate angular velocity to linear velocity, okay? And this relationship is given by this equation down here, where the linear velocity v is equal to the angular velocity times the radius. Now, this equation has two important concepts, and there's just a mistake that I want to draw your attention to. Radius is the distance from the center of rotation to the point being measured, and that will be measured not in radians per second, but in meters. Okay, so there's two important relationships that we can derive from this equation. Okay, so the first relationship is that linear velocity is directly proportional to the distance from the center of rotation. So v is directly proportional to r. Okay, so in other words, what it means is that a point at the rim of the rotating object, the furthest away from the center of rotation, will be moving the fastest. Okay, so that's important. And it's quite intuitive. Like I said earlier, I actually said it at the end of the previous video. If you're at the center of the circle, you have to travel a very small path to have the same angular displacement. So therefore, you can travel it much slower. Whilst if you have a bigger circle, to have the same angular displacement, you have to cover a bigger distance. And if you have a greater angular velocity, you will also have a greater linear velocity. And that's our second relationship. So our second relationship is that the angular velocity is directly proportional to the linear velocity. The bigger the angular velocity, the larger the linear velocity will be. Now, this linear velocity, I just want to show you there at the of a point on the rim of the, so basically the furthest away. That will be, we will call the tangential speed. So that would be the speed of a tangent line that we draw to a point on that circular path. That would be our tangential speed. Okay, now we haven't really spoken about directions yet. Now, when we have circular paths, we will sometimes say, okay, motion like this will be anti-clockwise, whilst motion like this will be clockwise. Okay, now, however, that's not really useful because it depends on your point of reference. And so they use the example of the Earth over here, where if you look from the North Pole, you will say it's spinning in one direction. And if you look from the South Pole, you will be saying it spins in the other direction. So it doesn't really work. And that's where the right-hand rule comes in for circular motion. Now, this right-hand rule says that the direction of an angular vector is the direction in which the thumb of your right hand points when the fingers of your right hand are curled in the direction of rotation. So basically, if your fingers is pointing in the direction of the rotation, then your thumb is pointing in the direction of the angular velocity. Okay, now here it's important they say that you should note that we've got directions for both linear velocities and angular velocities. Okay, they are velocities and not speeds, and therefore they are vector quantities which have both magnitude and direction. Okay, so our angular velocity has a direction which is given by the right hand rule, whilst our linear velocity is tangential to the path as illustrated in the diagram alongside. So my angular velocity, if that's the direction of my angular velocity, I can use the right hand rule to determine the direction of the angular velocity, whilst my linear velocity over there with the fly, my linear velocity will be the direction of the tangent to that curve. Okay, now you might say, but in which direction? Well, the fly is going around that way. So in other words, the direction will be in the direction that you are actually rotating. You can't make that direction for the linear velocity in the opposite direction. That would just be entirely incorrect. So it's not, don't overthink it. It's in the same direction as which it is rotating, but it's a tangent to that point. Okay, so that's in terms of your directions. And it's quite important that you take note of that. Now, we spoke about period and frequency earlier. And we said that period is the time for one revolution. Okay, whilst frequency is the number of revolutions per second. Now, if we go and we want to relate period and angular velocity, which we will do now, we can say the following. Okay, so they say we can substitute one full revolution into equation 54. Now, equation 54 said that our angular velocity is equal to our change in angular position over time. So if we have one full rotation, a full rotation is equal to 2 pi. That would be our change in angular position in terms of radians, would be 2 pi. So 2 pi, and the time for one revolution, that is period. So 2 pi divided by period is equal to your angular velocity. So in other words, your period then we can say is equal to 2 pi divided by the angular velocity. So this is one equation. And because this is true, the inverse of this equation would be equal to frequency, because period and frequency are inverses of one another. So from this then, we can then derive our equation for linear velocity in terms of period. And this then will be our linear velocity v is equal to 2 pi r, which is the same as, yes, that's correct, our circumference divided by time. And if you think of that equation, it's actually very simple, guys, because we say that average speed or average velocity is equal to the total distance divided by the total time in the case of speed, or the total displacement divided by the total time in case of average velocity. So if we have one full revolution, it will be that distance, which is the circumference of the path, divided by the time it takes to complete that one revolution, which is the period. So then it's just the circumference divided by the period. Very straightforward. Now, this derivation, it's important that you know this. You should be able to show how we can get our angular velocity in terms of period and eventually relate that to linear velocity. So in the next video, I will be dealing with the examples, example 36, which is dealt with on page 28.